high analytical deviations of mineral oil determination, toxicology and discussion on maximum residue levels. Before we start, I want to go with you through some terms and abbreviations that will be named within the presentation. First will be MOSH, which is the mineral oil saturated hydrocarbons. MOAR are mineral oil aromatic hydrocarbons. PAC or PAC will be polycyclic aromatic compounds, which are in principle MOAR with more than 2 rings. EFSA will be the European Food Safety Authority. FEDIO will be the European Union Vegetable Oil and Protein Meal Industry Association. LCGCFID is the coupling of liquid chromatography with gas chromatography and flame ionization detector. EN is European norm. LOQ is the limit of quantification. JRC is the Joint Research Center of the European Commission. Here's the agenda for today. First, I'm going to talk about the current situation, then go to current knowledge on toxicology of mineral oil compounds. Later on, talk about mitigation strategies, then the analysis of mineral oil and edible oils and fats, the observed deviations of these analyses, the fields of tension of the industry, and give an outlook at the end. What is the current situation at the moment? I mean, incidents like the contamination with high amounts of mineral oil in edible oil, like the incident in Ukraine 2008, have raised the awareness of producers and customers. Since then, this situation has triggered a number of measures in edible oil industry and analytical laboratories. Analytical methods have improved significantly since then, but are currently reaching their limits. Producers are now focusing on technical solutions for their plants, like the usage of H1, 3H lubricants, which are lubricants for direct or indirect contact with food, or planning the plant in such a way that you can minimize the contamination of mineral oil. MOAR with 3 to 7 rings are suspected to be carcinogenic at the moment. What do we know about the toxicology of mineral oil compounds? Here I want to cite some statements of the EFSA article of 2012, where they state that C35, up to C35, the body can accumulate mineral oil compounds, but above that, it's negligible. C16 to C35 MOSH, they may accumulate in the adipose tissue. MOAR with more than 3 aromatic rings, non or simple alkylated, they may be mutagenic and carcinogenic. EFSA had a risk rapid assessment in infant food formula in 2019, where they stated this again, that 3 to 7 PAC are MOAR components of main concern for their genotoxic and carcinogenic nature. But it is not possible to characterize the hazards in the absence of relevant dose-response data. Let's come to some mitigation strategies. The most obvious mitigation would be the prevention of the contamination with mineral oil compounds, but it's maybe also too easy to reach such a level. As you can see here in this graph, which is a courtesy of the German Federation of Food Law and Food Science, that shows the production of food in general. You can see that there are many points where mineral oil can enter the food. In each stage, from the raw materials on to the preliminary, intermediate products and final products, you can have contamination via just a simple contamination in diverse steps of the production. You can have migration from packages, or you can have also contamination via additives and processing aids. In this context, I would like to mention the FEDIO Code of Practice for the management of mineral oil hydrocarbons present in vegetable oils and fats intended for food uses. When you're a producer, you need to identify critical lubrication and fluid points. At all identified critical lubrication points, if it's applicable, you need to use only food-grade lubricants. If it's not possible, you need to implement a technical solution to avoid leakage or contact. you need control measures for the absorption oil of the hexane recovery system in order to minimize the transfer of mineral oil into the crude vegetable oil. The usage of steam and indirect heating systems is recommended because heating fluids can also contaminate your product. Another mitigation strategy would be like the deodorization of mineral oil compounds. But it has a certain limits. Let me show you this graph I created for you. I'm showing here the boiling point independence of the carbon number of N-alkanes. These red bars are the limits of the analysis method EN 16995. When you start to observe the boiling points of the N-alkanes and you see your results of mitigation strategies via deodorization, you can see here that C10 to around C25, it's easy to deodorize, MOSH and more. Starting from C25 on, it becomes very difficult to deodorize. Especially the range C40 to C50 practically stays in the product at the end after a deodorization. And as you can see here, in this boiling point range, you already would have triglycerides boiling point. So you can deodorize a certain amount, but the higher carbon number ranges will stay in the product. Other mitigation strategies would be like trying to remove more with activated charcoal, which is feasible for benzopyrene. Mitigation experiments have shown that the PAHs, like benzopyrene, they are removed. But take a look at the structures of more on the right side. More is practically not removed with activated charcoal. This could be because of this complex structure that more have. They have very long side chains, and this seems to make the adsorption not as effective as with PAHs. What can we say in total for mitigation strategies that we have observed in the last years? We have no significant reduction from MOSH above C25 with deodorization. We have hardly any removal of more with activated charcoal. Other agents, such as bleaching earth, they have little effect. So prevention seems to be, at the moment, the best way of mitigation. But every mitigation strategy that we are talking about requires the most accurate analysis results possible regarding the content of MOSH and more. This brings us to the next challenge, the analytic of mineral oil compounds. I will discuss with you 3 methods that are often used and discussed. Of course, there are more methods, but all of them have to prove themselves in proficiency tests. I'll go later through the presentation. First analysis method would be the ISO method 17780, where you can analyze MOSH from a working range from 50 to 1000 milligrams per kilogram. I just here show some steps of the sample pretreatment and measurement. First, you can solve the oils or fats, perform a cleanup over a silver nitrate impregnated silica gel column, then a pre-concentration and GCFID measurement. More is not possible to be analyzed with this method, and when I see the method here, we are working already in a very high working range, which the customers are not, they require far lower working ranges than 50 to 1000 milligrams per kilogram. Customers also require the information about more. So this method does not meet the current expectations at the moment. Other methods are based in the principle of the LCGCFID. The LCGCFID, what kind of instrument is that? It's in principle an HPLC combined with a GC. In this case, for the analysis of mineral oil and edible oils and fats, we inject our sample into an HPLC which has a silica gel column. We perform separation of fractions using an N-hexane dichloromethane gradient. So we fractionate MOSH and more and transfer these fractions into the GC. For the checking if we have collected the right fraction, we have certain markers like cholestane, TBB or perylene. Here shown on the lower side of this graph, you can see how the HPLC chromatograph would be. In this having just N-hexane, you will collect MOSH, and in the gradient N-hexane dichloromethane, you will collect more. After the fractions are transferred into the GC, the column is washed in the other direction as a backflush with 100% dichloromethane to keep your system clean. So this lowers your LOQ significantly compared to other offline methods. The next method I'm going to talk about is the method of Biedermann and Grob from 2012, which has certain more pretreatment options in order to reduce further the LOQs. For MOSH, you can have two possibilities of analyzing MOSH. You can just solve your fat and oil or inject it directly into the LCGC-FID. If you want to get rid of compounds like odd-numbered N-alkanes, you can solve your oils and fats, perform an aluminum oxide column, and separate these odd-numbered N-alkanes and perform the LCGC-FID measurement. For more, there are two pretreatment possibilities. First, solving your fat, epoxidating. Why is it also needed to epoxidate? Certain oils and fats have squalene and isomerization products of squalene, for example, or carotenoids and terpenes. And when you perform the epoxidation, you make them more polar and they are not fractionated to the MOSH fraction. So you can get rid of these interferences. And afterwards, you inject it to the LCGC-FID. Another possibility would be solving, epoxidating your sample, and then performing a pre-concentration and cleanup using silica gel column, and later on the LCGC-FID. A method that is now widely used by most of the laboratories would be the method from Florence Lacoste, the European norm 16995, which has even more sample preparation possibilities. For MOSH, similar as the Biedermann-Grob method and more, you can have just the solving and injecting for MOSH and more, solving and injecting to LCGC-FID, and yeah, also here like solving, epoxidizing, and LCGC-FID for more. You have here now two other possibilities for MOSH. You can solve your fat and clean up over silica gel sodium sulfate column and perform an LCGC-FID measurement, or solving and having similar as with Biedermann and Grob, using aluminum oxide column to get rid of odd number N-alkanes and perform the LCGC-FID measurement. For more, you can also perform a silica gel column pre-concentration and cleanup, and then the epoxidation, and afterwards the LCGC-FID measurement. This further reduces the LOQ, of course, but the limit of applicability of this method is 10 milligram per kilogram. Most of the laboratories now are working in ranges below 10 milligrams per kilogram, having LOQs at around 1 ppm. What can we say about all these techniques and methods? LCGC methods have widely become accepted. Offline methods often have higher LOQs. The pre-treatment possibilities are very good ways of lowering the LOQs, but it requires knowledge on the composition of the sample in advance. If it's not available, you need to perform several analyses for MOSH and several for more, which might take some days, and then you need to see what value corresponds, MOSH value corresponds to which more value, and which values are plausible. JRC has defined a decision tree for such possibilities in 2019 in the JRC guidelines, which I'm going to show now to see the complexity of the mineral oil analysis. This is the decision tree of the JRC, and as you can see here, when you get one sample, you have all these possibilities until you get to the results. You have here the extraction and at the end the result. Depending on the nature of your oil and fat, you need to perform several parts of this tree. And this might be also the possibility of why the deviations are so big in mineral oil analysis. The mineral oil analytics must meet the highest standards. You need very low reagent blank values, very clean LCGC system, and very well-trained staff, especially when you work in low concentrations. Plus, having too many degrees of freedom in the sample pretreatment almost inevitably leads to a high variance between laboratories. This shows up particularly strongly below 10 milligrams per kilogram in accredited interlaboratory tests. Let's come to the proficiency test results I'm going to show you. Here are the observed deviations in mineral oil analysis results. I'm showing now the 2019 DRRR proficiency test, which is an accredited proficiency test. And I wanted to show samples that are below 10 milligrams per kilogram to show the deviations that are at the moment. What can you see in this graph? In this graph you have here the mean value of the proficiency test. You have these two red bars, which are the acceptable deviations in order to pass a proficiency test, the so-called Z-score 2. When results are lying between these two bars, the proficiency test was passed with success. This sample, we are observing here MOSH C25 to C35, the samples 3 and 6. We can see here that with a mean value of 5.12 milligram per kilogram, we already have allowed deviations of plus minus 63%, which is even more than can be observed for pesticides proficiency tests. When we go further down the concentration, like in this case the sample 3 to 6, the MOSH with the arcane range C16 to C25, and we can see here that at 1.2 milligram per kilogram, one has already accepted deviations of plus minus 78%. The same applies for more. Observing more in samples 2 and 5, C16 to C25, we have here at a mean value of 1.37 milligram per kilograms, plus minus 75%. The next sample set will be samples 2 and 5, arcane ranges of more, C25 to C35. Here, at a mean value of 1.61 milligram per kilogram, you have plus minus 80% to pass a proficiency test. So a result having 0.33 milligrams per kilogram or 2.89 milligrams per kilogram would mean that you have passed a proficiency test. And when you observe most of the laboratories at the moment, which have a limit of quantification of 1 ppm or even lower, you can see that the in-between measurements between the laboratories would show also such a deviation in normal life. So what have we observed in mineral oil analysis results? Proficiency test results show a high to very high deviation below 10 milligrams per kilogram. The acceptable deviations, the so-called Z-scores 2, they are starting from 60% up to 99%. When in some cases below 5 milligram per kilogram, it's not even possible to evaluate a proficiency test because the deviations will be even above 100%. This also applies when you send samples to 3 or more laboratories. You will see that the repeatability within the laboratory is fine, but not the reproducibility between the laboratories. What are at the moment the fields of tension? Any strategy for minimizing mineral oil contamination is based on reliable results. So when you perform mitigation trials and you're sending samples to many labs, you will get very high variations below 10 milligram per kilogram, which is at the moment observed by many customers. And this nullifies all your efforts of minimizing mineral oil analysis. This situation currently leads to an uncertainty for both producers and customers. The ongoing discussions on more toxicology, like the statements that 3 to 7 packs are of main concern for their genotoxic and carcinogenic nature, but at the same time not being possible to characterize the hazards in the absence of relevant dose response data, further increases this uncertainty. I want to give an outlook on this whole situation. From my point of view, an optimized method for oils and fat is required, which is streamlined in the execution. From my point of view also, additional purification and cleaning steps should be performed systematically. The omission of certain purification steps for known matrices should not be at the expense of the specificity, giving, for example, false positive. We need also an at least semi-quantitative GC-GC method to estimate the amount of potentially harmful 3 to 7 packs. We also need research on the toxicology of the MOA fractions, especially the 3 to 7 packs, to establish dose response database action or even maximum levels. Thank you for your attention.